This video gives a brief introduction to connectors with timber and the way in which those connectors behave. First up, some nails. And I'm going to drive a couple of small nails into these pieces of wood. So this is a seasoned piece of timber, and you can see that as the nail has gone in, it's not caused a great deal of damage to the timber. This is an unseasoned piece of timber. Now it's friction between the nail shank and the timber that gives the nail its strength. If we think about what happens on a microscopic scale as a nail is driven into the timber, it is being pushed into the wood fibres like this, and it squeezes the wood fibres apart. So that as the nail is being driven, it just relies on friction between the nail and the wood fibres to give it strength. If we now pull these nails out, and I'll start with the seasoned timber, it takes quite a bit of effort. And if we pull the nail out of the unseasoned timber, we find that it comes out really easily. It's the lubrication of the moisture in the timber on the substructure that means that friction isn't quite as effective. And we find that nails have much stronger strength in seasoned timber than in the same unseasoned timber. Now we're going to have a look at screws. The Type 17 screw has a small cutout near the tip. That means it drills its way into the timber to start off with, and then as it goes further into the timber, these flutes on the edge of the threads cut their way into the timber structure. So let's see it in practice. As we drive this screw, a few pieces of wood chips come out as the head of the screw finds its way into the timber, and then as we go further into the timber, no extra material comes out. We've just got the flutes cutting their way into the timber structure and actually bonding with the timber structure. Now if we were to try to remove that screw, we have Buckley's chance. There's very, very strong withdrawal strength in screws, much higher than in the same size of nail. Bolts function in a completely different fashion. So in installing a bolt, we first drill a hole. And as we drill the hole, you can see a lot of fibre is coming out of the member. So drilling the hole produces a lot of sawdust. We have lost a lot of timber fibre in the member, so that the strength of the member is reduced. If we think back to the nail hole, no material came out, so that the strength of the member was not impacted at all by driving a nail. But whenever we install a bolt, we remove some timber from the member, and as a result we remove some of its capacity. Now if we install a bolt into that hole, the bolt is normally quite a tight fit into the hole, and that gives us good contact between the bolt and the timber. But I'll show you what happens on a smaller bolt so that you can see the way in which the load is transferred between the timber and the bolt. If this is a tension member and it's moving to your left, as it's moving to the left, the bolt moves to the right-hand side of the hole. That is where the bearing is happening. Now on our microscopic model, the fibres are like this and the bolt is pushing in this direction. It's pushing in the direction of strength of those fibres. So that is a very high bearing strength on the timber. On the other hand, if this is a beam and it's being supported by the bolt moves to the top of the hole and it's pushing on the wood fibre at the top of the hole. So what is happening here is that the bolt is pushing on the underside of the fibres across the top of the hole, and that is a direction of weakness of those fibres. So that the bearing strength of a bolt is much stronger where the loads are parallel to the grain in the timber, like this, than it is where the loads are perpendicular to the grain in the timber. So that while the strength of a nail and a screw is not a function of the direction of grain in the member, it is for bolts. And those two behave completely differently because of the way they transfer the load between the metal in the fastener and the grain in the timber.